Hello students, today we will be discussing simple harmonic motion, and in simple harmonic motion we will discuss how to solve problems. Now how to solve problems? The first step which is mentioned is identify the equilibrium or mean position of the particle and write its condition. So in this case we have a block, the mass is given m, the spring is having a spring constant of k. Now initially let's say that the block was at this location. So this is the mean position or equilibrium position of the block. So let's say in equilibrium condition the spring is stretched by an amount x naught. So writing the force on the block, it is mg downwards, kx naught upwards. So we have the equilibrium condition is kx naught minus mg is equal to 0. This is the first equation which we get. Now between this, the second step says displace the particle by a small distance from its equilibrium position. Let's call it as extreme position. So here we are displacing this block by a small distance, and let's say that this is the extreme position of the block. The third statement says release the particle and between its mean and extreme write the force equation. So between this mean and extreme, somewhere here we will write the force equation. So let's say the extra length by which the spring is stretched is x. So it is the spring force acting on this block is kx plus x naught, and downwards the force acting is mg. So the net force which is acting in the upward direction, यहाँ पे देखो जो force इस upward direction में लग रहा होगा towards mean position, that force will be equal to k x plus x naught minus mg. So this is the force which is acting towards the mean position. This is the force acting towards the mean. Okay. We can also call this force as the restoring force. So we have the restoring force as kx plus k x naught minus mg. So these two they cancels out because it is 0. So we get the restoring force as proportional to x. We get the restoring force proportional to x. In terms of vector, if I write, it is F vector restoring is equal to minus k x vector. Now what is this x? This is the displacement of the particle from its mean position. X vector is the displacement of the particle from its mean position. This is the displacement of the particle from its mean. Okay. Since the displacement is downwards, why this negative sign? Since the displacement is downwards and the force is acting upwards, so we will write here a negative sign. Now equating it to mass into acceleration, because the force will bring mass into acceleration. So it is mass into acceleration. It is a vector is now equal to minus k by m x vector. The standard equation for SHM is a is equal to minus omega square x vector. So comparing these two equations, we get omega as root of k by m, and hence the time period of oscillation will be given as 2 pi by omega, which is 2 pi under root of m by. Okay. So this is how we find the time period of particles undergoing SHM. Let's apply the concept of problem solving which we have just studied in this particular topic, that is oscillation of a floating body. We have a block of mass m and area of cross section A which is floating in a liquid of density rho. Find the angular frequency of the block for a small vertical disturbance. So this is the block and the mass of the block is given to us as m. The cross section area of the block is given to us as A, and initially the depth which it is inside the liquid is x naught. The length of the block which is inside the liquid is, let's say it is x naught. The density of the liquid is rho. So in equilibrium condition we have the force equation as mg downwards and the buoyant force Fb upwards, right? The value of this buoyant force will be what? It is equal to the weight of the liquid displaced. So the volume of the liquid displaced is A into x naught. The weight of the liquid will be rho, the density of the liquid is rho, multiplying it by Ax naught, we get the mass of the liquid displaced, multiplied by G is the buoyant force Fb. So in equilibrium we have mg minus A x naught rho g is equal to 0, or simply we have x naught is equal to m upon A rho. This is from the initial condition, right? In equilibrium condition. Now let's say that the block is further displaced by an additional amount x. So it is pushed inside the liquid by an additional length x, right? So this is the new location of the block. Now the forces will be, mg will keep on acting downwards. The buoyant force now changes to Ax naught rho g plus Ax rho g. Okay? So now we have the restoring force as F restoring, which is equal to the new buoyant force, which is A rho g x plus x naught minus mg. This is the new restoring force. So finally the restoring force comes out to be, on solving the above equation, we get F as A rho g x. If we want to write it in terms of vector notation, it is F vector is equal to minus A rho g x vector. Equating it with m omega square x, equating it with m omega square x, we get omega as root of A rho g by m. This is how we can solve these type of problems using the concept of problem solving which we have just studied, right? It's a wonderful concept if you apply it in the same method which we have studied. Okay? Thank you.